The last time we ended our discussion on the four fundamental principles that would be essential in understanding of how uh, materials could influence our applications. The first thing is that your structure, which is the part that governs your properties, would essentially depend upon your processing conditions, and your properties would essentially affect the performance of your material. And we looked into the example of alumina, where three different structures were processed three different ways and having three different optical properties. Moving on, we'll now look into the three broader categories of materials that exist. The first one is metals, and as the name says itself, it is made up of one or more metallic elements. The material iron, aluminum, copper, steel is a alloy of two components, which is iron and carbon, still a metal. The generic characteristics of metals include stiffness. They are strong, yet they have good ductility. They have got good conduction for electricity as well as heat, and they're not transparent to visible light. General characteristics of materials belonging to the category of metal. Then comes the important category of ceramics. Ceramics, they are compounds between metallic and non-metallic elements, and they are commonly oxides, nitrides, or carbides. These are normally characterized as uh, ceramics. For example, the the material that we learned about in our earlier class, alumina or Al2O3, it's a ceramic. Similarly, silicon oxide, silicon nitride, they are all ceramics. General characteristics, they have very good stiffness and strength, and the strength and stiffness are comparable to that of metals, and they are very hard. Historically, they have been known for their brittleness, that they're very brittle in nature. They're not as ductile as the metals. However, new ceramics, they have improved the fracture resistance, or the resistance to their brittleness. It has improved to an extent, but still they are categorized as brittle as compared to metals. Again, typically they have low electrical conductivities, and they are more resistant to high temperatures and harsh environments. So ceramics, mostly they are used for applications which require uh, high temperatures. For example, your furnaces, they have the insulation made up of alumina, which is a ceramic. So high temperature applications, or applications that require resistance to harsh environments, ceramics are normally used in those environments. The third category is polymers. I'll recommend your name in the chat section. I'll not mark attendance based on that. So don't waste your time. The third category is that of polymers, and polymers are made up are organic compounds that are chemically based on carbon and hydrogen, and some other non-metallic elements, oxygen, nitrogen, silicon. They are known for their low densities or good weight to strength ratio, nor as stiff as strong as other material types. They are extremely ductile and pliable. That means they can be easily formed into complex shapes. Relatively inert chemically and unreactive in most of the environments. That's what make polymers more useful these days. Uh, these are the three broad categories of materials that you should have the basic understanding of. Our focus mostly would remain around the metallic systems, although we'll have uh, a discussion on ceramics, polymers, and composites at the end, but primarily we'll focus on metals as they're mostly used. Uh, Now, moving on towards some of the basics of high school that you must be familiar with, uh, electrons in atoms. The original or the traditional simplified Bohr atomic model represented that electrons are assumed to revolve around the atomic nucleus in discrete orbitals, and the position of any particular electron is more or less well defined in terms of its orbital. That is also discrete. That means the energy states they do not vary continuously with energy, and there are finite energy steps that are there within the uh, electronic structure. For instance, if you look at this original model, you have a nucleus over here, and at a certain distance from a nucleus, you have the first orbital that would contain the electrons, and similarly the second orbital and third orbital. And this orbital would have a finite energy as compared to this orbital and this orbital, but there would not be any energy levels in between. So there would be discrete energy levels, and electrons would be quantized at different energy levels. This was the original or simplified Bohr atomic model. But later on, the wave mechanical model, it indicated that electron exhibits both the wave-like nature and the particle characteristics. That means electron is having this movement of wave-like nature present within itself along with the particle nature. Uh, this means that electron can moving in a discrete orbital. The orbit or the electron moving within this orbital is only a portion of it which is correct. It also means that electron is essentially moving in a wave-like around a certain. So this electron motion is actually depicting both the particle-like nature and the wave-like nature, and this makes the fact that that stemmed from this wave-like nature. In other words, position is then described by the probability distribution or
सर आपकी आवाज में
electron
डिस्टॉर्शन आ
cloud.
रही है।
How do you
Yes, sir.
अभी आ रही है, ये शुरू से आ रही थी?
Yes, sir.
हाँ सर अभी आई है, थोड़ी देर हुई है सर।
देर होगी।
Is it better now?
यस सर अब ठीक है।
Yes, sir. अब ठीक।
All right. Great. So what it says is that the initial model stated that from a certain distance from the nucleus, there was an energy level where the probability of finding the electron was 100%. At a certain distance from the nuclear, which was the orbital, electronic orbital, you had the possibility of finding the electron 100%. But as we discussed the wave nature of particle, we see that as we move away from the nucleus, the probability of finding the electron increasing until you reach to a certain distance, and then it decreases. But it's a probability distribution of finding the electron within this zone around the orbital. So uh, this is the distribution, or this is the region in space in which you can have an in which you can have the probability of finding an electron away from the nucleus. Now, based on this phenomena, which is the wave-like nature of electron, uh, we have defined the electronic configuration in terms of quantum numbers. So quantum mechanical model, it is a model which describes the position of every electron in an atom, and it is
Sir, again
described the
distortion is
has
coming.
potentials are known.
सर बहुत ज्यादा आ रही है सर.
डिस्टॉर्शन ज्यादा आ रही है अभी.
सर आपकी आवाज कट कट के आ रही है.
यस
यस
सर.
सर काफी आ रही है.
क्या जी सॉरी नहीं आ रही सही.
यस
No,
सर
sir, नहीं
डिस्टॉर्शन काफी आ रही है आपकी आवाज में.
नो सर नहीं सही आ रही, कट कट के आ रही है.
All right. Let me get my internet connection checked up, and then I'll start with quantum numbers again. Just give me a minute. All right.